All right, we're up.
Okay. Hi, everyone, and welcome to this week's Quantum Chaos Seminar. This week, it's my pleasure to introduce the speaker, Fiona Burnell. Fiona is assistant professor at the University of Minnesota and currently on sabbatical at the Institute for Advanced Study in Princeton. So she got her PhD from Princeton University and went on to do a postdoc at All Souls College in Oxford. She's won various grants and prizes during her academic career, including a Sloan Fellowship and an SFS Career Grant. She's done a lot of really interesting research into exotic quantum phases of matter and quantum dynamics, what she'll be talking about this week. And it's my pleasure to introduce Fiona. We'll be talking about exact models of many-body quantum scars. All yours.
Okay, thanks. So thanks for the invitation to speak, and thanks for listening. And yeah, I'm going to tell you about some recent work in collaboration with Vedika Kamani, Nicholas Odia, who's a student at Stanford, Vedika is a professor at Stanford, and Anusha Chandran, who's a professor at Boston University. Okay, and so in the first part of my talk, I'm going to try and tell you, for those of you who don't know, what is a quantum scar and why I think they're interesting, okay? And so I'm going to kind of, just to put this in context, this is a question about, what can happen in the dynamics of closed quantum many-body systems, right? So the topic of this seminar. And so, the two kinds of questions that we generally think about for this kind of dynamics is, how does the system, thermalize or evolve in time, or maybe not thermalize? And in particular, and I think this is particularly relevant if you're, have in the back of your mind applications, for example, to quantum information. The question is, can there be situations where there's information that just won't be lost? When my system is kind of evolving under its own dynamics at finite temperature. Okay, so what do we know can happen in the dynamics of closed many-body quantum systems? So option one is that the system will always thermalize. And so I'm not going to say too much about this. This is kind of the standard picture. It occurs in lots of, kind of generic interacting condensed matter models. Also, people on the high energy side think about ADS CFT models of space-time. Those are always thermalizing. Okay. And this is kind of what you generically expect. I take my quantum system, even though it's closed, and it evolves under its own dynamics, okay? And so now you might wonder, well, how does that happen, right? And for example, maybe my universe started in a, in an eigenstate. So how is it that we locally measure thermal equilibrium? And the answer to that question is that, you're not like measuring the entire universe, you're looking locally. Okay, and so basically, when we look at quantum mechanical systems that thermalize under their own dynamics, the intuitive, the kind of picture of this is that locally the eigenstates look pretty random, or more specifically, pretty thermal, right? So this is the eigenstate thermalization hypothesis, and so let me just remind you of the kind of technical way that we define this. So in order to parameterize, what my local observer is seeing, I divide my system into some region A, which is what I can measure, and then the rest of the system, which is B, okay? And any local properties in A are kind of captured by this reduced density matrix in A. So I trace out subsystem B, okay? And then, basically, the eigenstate thermalization hypothesis says that this reduced density matrix of subsystem A should look thermal. Okay, so what does that mean? It means that if I calculate the expectation value of some observables that are local to A, right? And so, sorry, and I should say, this is a reduced density matrix that's calculated with respect to some eigenstate here. So psi is some eigenstate, okay? And so, observables that are local in A are going to look thermal, okay, as long as this eigenstate has finite energy density. And if I calculate an entanglement entropy, okay, between subsystem A and the rest of the system, so the entanglement entropy is just trace rho log rho, okay, that this is going to be extensive in the size of A. Okay, and so these are kind of metrics that we use to say that for an observer in subsystem A, everything looks thermal. And again, this is kind of what we generically expect for closed quantum systems. Now, option 2, possibly, and there's now some new controversy about this, well, the most famous example of this, but option 2 is that the system will never thermalize, okay? And so this is the case, for example, for integrable systems, but also, kind of the most famous example of this is many-body localization. And so the idea of many-body localization, and I should say that there have been some recent works which cast into doubt whether this, really is a robust kind of dynamical phase of matter. But the idea is basically that I have a system in which I have extensively many local conserved quantities, right? So energy cannot flow effectively from A to B, okay? And in this case, basically the system will remember forever some of the information about subsystem A, right? So, right. And so in this case, basically all eigenstates are non-ergodic. And many-body localization in some sense is a very particular example of a more general phenomenon, which is integrable systems. Okay, and I'm not going to say too much about these except to say that in both of these examples, what's going on is you have extensively many conserved quantities, and you find that in fact, like all eigenstates in your system are non-ergodic. Okay, so that's option 2. Okay. And this means actually that generic initial conditions will fail to reach thermal equilibrium. Okay, now option 3, which is what I'm going to talk about today, is that the system will almost always thermalize, but that there are some very particular initial conditions in which it will not thermalize under its own dynamics. And in fact, the models that I'm going to tell you about today are models where we can show exactly that in certain initial conditions they never come to thermal equilibrium. They have sort of persistent oscillations that last for all time under their own dynamics. Okay, so in particular, and so this is what we call quantum scars. In particular, I'm going to have exponentially many thermal eigenstates. So L is going to be my system size, and the number of eigenstates which look like they satisfy ETH is going to be C to the L, where so basically grows, basically with the Hilbert space size. But in this, very large Hilbert space, there's some number of states that grows polynomially with the system size, which are going to violate ETH. Okay. And so let me just make that a little bit more detailed by telling you about the specifics of the setup that I'm going to treat today. So all of the models I'm going to talk about today are going to be one-dimensional. And so I'm going to have a spin chain with L sites, okay? The spin on each site is going to be S, and so I'm going to have 2S plus 1 states on each site. So the size of the total Hilbert space goes like 2S plus 1 to the L, okay? And I'm going to have some Hamiltonian, which I'm going to require to be local, okay? It doesn't need to have any other symmetries or fancy properties, and in particular, it doesn't have to have spin rotation invariance. Okay.
So Fiona, there is a question in the chat,
Yeah.
sorry, which is just related to one of the previous slides.
Yeah.
That if whether, away from the thermodynamic limit, you would expect option 3 to be the common situation in many body systems, in the finite dimensional case, away from the thermodynamic limit.
So the question is that what we would expect to happen here?
If option 3 should be expected to be the common situation away from the thermodynamic limit.
A common situation. So I think that depends a lot what you mean by common. So I think what the main kind of message of the story that I'm going to tell you is that this is not super hard. It's not super hard to construct models that do this. However, these models are fine-tuned, and so let me say that, you know, so I guess I haven't sort of told you how these scars differ, okay? But so basically the thermal states, you know, one thing that we can look at is the entanglement entropy associated with cutting the chain in half, okay? And so for these thermal states, that's going to grow with L, okay? For the scar states in the models that I'm going to describe, it's going to be bounded by, like, it's going to grow not faster than logarithmically with L, okay? So, which is to say, even if you're studying fairly small Hilbert spaces, you know, like what you can do with exact diagonalization, you can sort of clearly see that the scar states are different from the other states, okay? So this is not something that, you know, you plug in your favorite, you know, Hamiltonian and you expect it to pop up, okay? However, it actually does occur, you know, it's an exact feature of a surprising number of, you know, models, some of which are very familiar to us.
So that there is a kind of a follow-up that in which he's asking that the states near the ends of the spectrum do not thermalize, and whether they qualify as scars.
Okay, very, very good. Yeah, good. So this is something that maybe I didn't state clearly. So yeah, so in order for us to call something a scar state, we would like it to have finite energy density. So yeah, so, you know, the eigenstate thermalization hypothesis kind of only applies to states with finite energy density. And of course, in finite system, you know, you kind of want to truncate the energy density that you're looking at. You know, you don't want it to be a very small energy density. But so these are states that are going to be at or close to the middle of the spectrum. So at an energy density that corresponds to very high temperature.
Okay.
Like, for example, like infinite temperature. Yeah, so that indeed, that's a very important kind of feature. Yeah.
Okay, thank you.
Okay, cool. All right, so yeah, so we're going to be working with these spin chains. And okay, so, and you know, what are we going to look at to ask whether our system looks like it has quantum scars? Well, we're going to cut the chain in half. Okay, we're going to, you know, compute the reduced density matrix of the left half, and we're going to compute the entanglement entropy, okay, between left half and right half. Okay, and yeah, so here's sort of a picture, which I think speaks to what the previous question was getting at. Is, so, you know, here's a typical ED plot for these kinds of systems. So this is energy density, this is entropy, this is for one system size. I actually forget exactly the number of sites in the chain. It's, you know, something like 14 or something. Okay, and so up here, what we see is this narrow band of thermal states, okay, where, you know, the entropy scales like the thermal entropy. And if you did this for different system sizes, you would see it scaling like L, okay? And then down here, so you can see that we have some, in this model, we have a couple of spurious low entanglement states. But here in particular, we have some states that we have sort of explicitly constructed to be scar states, and these have entanglement that scales not faster than logarithmically with L. Okay, so these are the kind, you know, this is the kind of diagnostic that we're going to use when we're thinking about this. Good. Okay. And so, all right, so that's kind of what we're talking about, is basically a Hamiltonian with a spectrum that in which almost all of these states look thermal, as measured by the entanglement entropy. You can also check level statistics. So level statistics of these systems, since there's so many more thermal states than scar states, also look thermal. Okay. But, you know, we can see when we do these entanglement versus energy density plots that we do have some eigenstates that are clearly not thermal. Okay, and so I'd like to address a few questions. So, you know, first of all, do Hamiltonians in which, you know, this is an exact phenomenon, meaning that I can show that I have such low entanglement states for every L, and the limit that L goes to infinity, do these exist? And the answer, as you might surmise, is yes. And I'll give you some examples. I'll tell you why I think that's interesting. And then I'll tell you a bit about what is the structure of these models, and how we can construct them. And at the end, say a few words about how fine-tuned they are. Okay, so actually, let me start with an obvious question, which is, why should you care? Why should you be interested at all in finding a model with this property? And so, to play devil's advocate, the reason that you might be skeptical that this is ever a physically interesting phenomenon is that, again, the size of the Hilbert space is some constant to the L, and the number of scar states is polynomial in L, right? And so you would say to yourself, well, this is such a tiny fraction of the Hilbert space. How am I ever going to prepare my physical system, okay, in some state where I'm going to observe the effects of these quantum scars, right? It seems like a tremendously unlikely thing. And so, and tremendously unlikely means that, as L gets big, as you might expect it to in your lab, this becomes a set of measures 0. So why would you bother, understanding these quantum scars at all if you're never going to observe them? Yeah.
So sorry to jump in again. So there is a question about a previous slide, and the question is, what is the difference between the scarred states and the spurious states that you were showing in the plot?
Oh, okay, yeah, right. So yeah, so why do we circle these as scar states? So in these, so these ones are circled simply because, so this is a model. I haven't explained the model yet, but these are states for which we can prove that there is, for every L, there is a state, so corresponding to these guys as identified by certain quantum numbers, et cetera. There is a state that has entanglement that's bounded by log L, okay? These other states are also states that have low entanglement, but so they're not circled because we don't understand them analytically, right? And so in particular, these ones, I don't know for sure whether these are gonna persist for all L, okay? But they could, right? So there could be scar states. It could be that there's a few scar states in this model that, we just don't understand why they're there analytically. Yeah, but indeed, by the definition of sort of looking at the entanglement, you would say, well, these ones also, are non-thermal, and that's certainly true. Okay. Yeah. Okay. So why should you care? And so I think the paper that really the thing that really got people interested in this started with an experiment out of Misha Lukin's group, which I'm sure many of you are familiar with. So the details of the experiment are not at all important for this talk, but basically they took a chain of Rydberg blockaded atoms, which you can think of as a two-state system, okay? And they prepared it, so let's a two-state system, let's call it the state spin up and spin down, okay? They prepared it in an initial state that it looked like up, down, up, down, up, down, up, down, okay? They watched it evolve in time, okay? And what they saw, and I should say there's a Hamiltonian here, the details of the Hamiltonian are not important for this talk. But what they observed, okay, were these persistent oscillations in spite of the fact that under the, with this Hamiltonian, this particular state is a very high temperature state, okay? So you would expect it just to thermalize very quickly, okay? And instead they saw these persistent oscillations. And so the conjecture, and this is sort of the paper which introduced, I think, the notion of quantum scar in the many-body context in its current kind of incarnation to the condensed matter community was a theoretical paper that proposed that perhaps this is happening because the initial state, this antiferromagnetic initial state, actually has some large overlap with quantum scar states, or which in this model may or may not be exact. Well, are probably not exact, but things that are close to quantum scar states. And so this is very significant because it tells us that, at least in some situations, even though the set of scar states is very, very small, it could just be that, or there are some situations where it could be that certain states that are easy to prepare initially in the lab happen to have large overlap with your quantum scar states, and then you can see these really striking non-thermal phenomena. Okay, so that's why you should care. Okay, so so this is just what I just said, that this very small set of states could have a large overlap. Okay, and so this can be experimentally interesting. Okay, so with that motivation, let me tell you a little bit about what is the structure of quantum scars and how should we find them. Okay, and so there's a few papers on this, and I'm going to focus on our own perspective, which is that a nice way to think about where quantum scars come from is to actually think about, first of all, systems of symmetry. So imagine that I have some Hamiltonian, I'm going to call it HC, that has a non-abelian symmetry. So think a Hamiltonian with, say, spin, rotation, and variance. Okay, so if I start with such a model, it's certainly, I have, multiplets of different total spin that are not going to mix at all. Okay, so my Hilbert space is sort of broken into different symmetry sectors. And now I'm going to think about adding two kinds of terms. So first of all, I'm going to add a term, I'm going to call it HS, okay? And this is going to be some term whose job is just to make sure that my scar states are not all energetically degenerate, okay? And then I'm going to add another term, which I'm going to call HA, and I'll tell you more about HA in a few minutes. But basically, the idea is I'm going to add a sort of special symmetry breaking term that's going to break the symmetry generically, but sort of more or less preserve it on some subset of eigenstates. Okay, and so let's just start with the model that has symmetry, right? So imagine that I have spin rotation symmetry. Then I know that my Hamiltonian is block diagonal in all of these blocks with different total spin, okay? And now many of these blocks are very big, right? They're exponentially large in the Hilbert space, they're exponentially large in the system size, okay? But some of them can actually be quite small. So for example, so for example, the highest spin representation is one that's quite small, okay? Now, if I wanted to, ask, is my system with a non-abelian symmetry, is it thermal? What I would look for is not obviously for the Hamiltonian to be thermal as a whole, but instead I would look for ETH within each block, right? But of course, some blocks are small, so some blocks have only order L, or L to some power states rather than exponentially many states in L. And so for these little blocks, actually, thermal entanglement does not grow linearly with L because there's not exponentially many states in here. Okay, and so the idea is let's exploit this to break symmetry in a particular way. Okay. Such that we can have exact quantum scars. Okay, so here's what I'm going to do. So let me sort of walk you through the simplest model with SU2 symmetry, which is, let me take a spin chain with spin S and some number of states of sites L, okay? And let me consider, so I have sort of what I'm going to call a base state, which is the state where all of these spins have, the minimal SZ, okay? And then let me consider the sort of the multiplet of states that are in that, that are created by raising the spin of these guys, okay? So I'm going to define an operator Q plus, which is just going to raise the total spin by 1, okay? And so now this generates n states, or some number of order L states, okay? And this is in fact all of the states in this highest total spin multiplet. Okay. And so from the point of view of this construction, right, if I have a symmetric Hamiltonian, well, all states in this multiplet have the same energy. Okay. So now let me consider adding a term that's, for example, proportional to SZ. Okay. And so that's not going to actually, do very much to the Hamiltonian of the system, but it is going to lift this degeneracy. Okay, so now I'm going to kind of change this sort of tunnel of degenerate states into a tower of states with different energy. Okay, and this gives me nice sort of equally spaced energies, which is convenient if I want to see oscillations. Okay. And now what I would like to do, okay, is I would like to break the symmetry in such a way that this symmetry breaking term is going to actually annihilate all of the scar states. Okay, and so one way to do that is I can put in HA anything that projects a pair of neighboring spins onto some sort of state of non-maximal total spin, right? So to get the maximal total spin, each pair of neighbors has to be in their maximal spin representation. So it's easy to identify a bunch of operators that could go into here. Okay. And okay, so this operator HA, we wanted to just annihilate all of the scars. Okay, this guarantees that all of my scar states are eigenstates, right? And they have these energies that are equally spaced by some amount, omega. Okay. And in addition, they are sort of naturally low entanglement states, because what have I done? Well, I've taken my Hamiltonian that was block diagonal, but now I broke the symmetry, but I broke it with an operator that annihilates just this highest spin tower, right? And so basically, most of my Hamiltonian is this one big block of thermal states, right? Which now look thermal in the generic sense without the symmetry. But I've sort of preserved this little corner down here of scar states, okay? So here's an example of a Hamiltonian that does this. I wrote this up because you can see that this is not a terribly unnatural Hamiltonian to write down for a system, okay? And this is a Hamiltonian that sort of singles out this Hilbert space and has exact quantum scars. Okay, so I should say that this idea of getting scars from SU2 symmetry in this way was actually already present in the original kind of many-body quantum scar paper by Ari Turner and company, and was also this model in particular was discussed in a paper by Mark Lin and Matrunich earlier this year. So this was sort of, this idea was not, original to our work, but I like this because I think it's the simplest kind of example of how symmetry works in these systems. Okay, and so this illustrates one. So when you see these pictures of quantum many-body scars, it's a little surprising, and you might think to yourself, well, how on earth would I get such a thing, right? And this example shows that one easy way to generate this is basically to start with a symmetry, right? And break that symmetry in such a way that you pick out a small symmetry multiplet, okay? And kind of isolate that from the rest of the Hilbert space. Okay. So once you sort of understand how to think about symmetry as a way of generating quantum scars, you can see that this particular example can be generalized in many ways. So how can you generalize it? Well, the first thing you can do is you can change the sort of ladder operator that takes you between the different states in the scar tower. For example, I could, instead of acting with the many-body S plus, okay, I could act with an operator that takes S plus to some power and let me first here talk about S plus to the 2s on each site, and adds those up, possibly with some relative momenta between sites, okay? And now I can start with the same base state of, this sort of maximally polarized in the -z direction, and think about creating a tower of scars from this state here, okay? And it turns out that, so this operator, Q plus, you can also think of as a generator of an SU2 symmetry, okay? So you can, it's not spin SU2 symmetry, but you can think about having a Hamiltonian HC, which is invariant under this new SU2 symmetry, okay? And you can basically play the same game, okay? Again, I can lift the degeneracy of the scar states just by adding an SC term to my Hamiltonian. And I can identify, using essentially the same algorithm, an HA, which annihilates these scar states, but breaks the this SU2 pseudospin symmetry on the rest of the Hilbert space. Okay. And so this is this model here, and this was pointed out by Mark and Matrunich, as well as a paper by Sanjay Mugdalia and also Andrei Brnovic's group, that this models of this form are relevant for understanding quantum scars in a model. It's called the Hirsch model, but it's very closely related to the Hubbard model. And so this kind of SU2 symmetry in the Hubbard model was observed long ago. And you can tweak the Hubbard model and get quantum scars. And in fact, you can think of those quantum scars as arising from exactly a Hamiltonian of this form. Okay.
So there is a related question, Fiona,
yeah.
In the chat. That is, how do you know that the scars are forming because of the presence of the SU2 symmetry? And can any system which possesses SU2 symmetry show scar states?
Okay, yeah. So actually, let me go back and say a couple of things again. And hopefully clarify, and please let me know if it doesn't clarify. So, okay, so when I start with a model with SU2 symmetry, okay? And so you can say, what does it even mean in the presence of a symmetry for this model to be thermal, right? And so, because my Hamiltonian is block diagonal, right? I have these blocks of different total spin. So what it means for this to be thermal is that within each block, things look thermal, right? So, if you're a numericist and you're looking for ETH in a model with SU2 symmetry, you first diagonalize by spin sector, and then you do your level statistics, et cetera, in a given spin sector, okay? So when the model has SU2 symmetry, even though there are these little blocks down here that are kind of isolated by the symmetry and have low entanglement, we don't actually call them quantum scars. We just call them, small blocks that are isolated by the symmetry. Okay. So the idea is that if you start with a model with say SU2 symmetry, okay, and you break the symmetry in this particular way, okay? So I'm going to break the symmetry, but I'm going to break it using an operator that actually annihilates. So these psi n's, okay, are like all of the states in this highest total spin representation down here in this little tiny block, okay? So I break it with an operator that annihilates all of those states, okay? And so in particular, so the picture looks like this. So this operator, because it annihilates all of these states, it doesn't annihilate these guys up here. So now this, most of the Hamiltonian goes from these block diagonal pieces to something that's just a generic, matrix with lots of off diagonal elements between all different spin representations, okay? But it does keep this highest weight spin representation singled out. Does that answer the question?
I thought it did, but we have some delay with the YouTube, so I'll let you know. I thought it was a very good explanation.
Okay.
We do have a few more questions, but they are more general. Maybe we can leave them for after the.
Okay. Sure. Yeah. So right. So one thing we can do is we can think about more general sort of ladder operators with the same principle. We can also construct models in which we change the symmetry group. Right, so, and this is actually one of my favorite examples. So I can take SU2 and I can replace it with SU3, okay? Now, what does that mean? Well, this is a statement about operators, but you can think of this as something that you could do when you have 3 states on your chain, okay? So SU3, the fundamental representation has 3 states instead of 2, okay? So think about, you know, kind of a spin 1 chain with some operators that maybe look a little different than what we usually put in, okay? But, okay, so now there's an analog. So if I play with, you know, SU3, for example, there's an analog of this state where all of the spins point down, okay? It's called the lowest weight state. And in the same way that we have spin raising operators, so like S plus and S minus, so for SU3, I actually have 2 different sort of raising operators, okay? And so I can generate a tower of states by acting with these 2 raising operators on this lowest weight state, okay? And this tower of states, in fact, for general SUN, you know, it has like not more than polynomial and L sort of states in it, okay? And so now to sort of add the other terms in our Hamiltonian, what do you do? Well, now I have sort of, just as I have 2 different raising operators, I have 2 different operators that are, you know, kind of analogous to SC. And so I actually have, in choosing my Hamiltonian that's going to tune the energies of the scar state, specifically, I now have 2 parameters instead of just 1 parameter. So I have A1, A2 instead of omega. And then the final piece is to pick this part of the operator that's going to annihilate my scar states. And again, so basically, just as if you wanted to project onto the Hilbert space orthogonal to the space of highest total spin, so here what you, for 2 sites, okay, so here you want to project onto the Hilbert space that's orthogonal to, you know, a totally symmetric representation of 2 spins, okay? And that is sufficient to give you something that's going to annihilate all of the states in this representation, generated by acting with powers of these Q plus 1 and Q plus 2 on psi naught, okay? And so here's a picture of what you get for this model, okay? So there's these states now have 2 numbers associated with them. N is the power of this sort of raising operator 1, so, you know, operator 1 that's like S plus, and M is the power of operator 2 that's like S plus, okay? And so the colors here indicate, you know, the value of, now I forget, I think it's either M or N, and I'm actually blanking on which one it is, but so, you know, let's say it's M, okay, so all of these red ones are in the same multiplet of M, right? And then if you now change N to N plus 1, this pile of states moves over here, okay? And you can see that we have sort of these 2 different frequencies, one associated with N and one associated with M, okay? So that's a fun kind of model. And let me just take a minute to talk about the dynamics of these systems. So, one of the fun things, okay, about this SU3 model is that I naturally can introduce 2 different frequencies, okay? And that allows me to get some more exotic dynamics of initial states. So one of the features of these models, I said at the beginning that one of the things that's interesting about quantum scars is that sometimes the scar Hilbert space, you can arrange it to have, you know, a very large overlap with a set of states that you could prepare experimentally. So in particular here, there are certain product states that live entirely in the scar Hilbert space. Okay, so here's an example. This is just a product over a particular, you know, superposition of, you know, so this is in a spin 1 notation. So plus you should think of as SC as plus 1, 0 you should think of as SC as 0, and minus you should think of as SC as minus 1. This is just a particular product state, okay? And you can initialize it, and you can look at, this is its time evolution under this scar Hamiltonian. This state lives in the scar Hilbert space. And basically, depending on exactly the state that you choose, you can get, you always get sort of these perfect revivals, although you can actually change their period and get a variety of kind of exotic behaviors. Okay. And so now let me look at how I'm doing on, okay. And so, yeah, and I should say, you know, you can do this kind of thing with SU2 models as well, that I really want to emphasize, these are exact eigenstates of the Hamiltonian that don't, you know, that kind of live entirely within this sort of highest total spin or highest weight multiplet and don't mix with the other space and the other states in the Hilbert space. And so we see these perfect revivals of their dynamics. So this persists to infinite time. And, you know, this is a feature of these Hamiltonians in the thermodynamic limit. So there's no, you don't need, yeah, it's not a transient phenomenon, it's not a finite size phenomenon, and that we can show analytically. Okay. Other generalizations, if there are people in the audience who like integrable models, maybe you like to think about Cutiform symmetries, okay? So Cutiformed SU2 is a bit like SU2, but you deform the commutation relation of Q plus and Q minus, okay? And I don't want to sort of dwell on the details here for those of you who haven't seen these symmetries, but this is sort of a modification of SU2 symmetry, and we can once again define operators Q plus, which are the analog of an operator that sort of raises the total, you know, total SC of the chain. And you can use almost exactly the same construction, which is you can make a scar tower starting from the lowest weight state in a representation of this symmetry. And you can obtain a Hamiltonian by actually just Q-deforming the operators in the Hamiltonian that worked for our SU2 example, okay? So we can make scars, even though this is not sort of a usual Lie group symmetry, these Q-deform symmetries, we can basically follow exactly the same steps and again, make Hamiltonians with exact quantum scars. Okay, so let me sort of take a step back and just summarize what we've seen so far. So the first thing is, you know, where do we find scars? So they arise actually very naturally when we think about breaking a non-abelian symmetry, or in fact, if you like, a Q-deform symmetry, but we have to break this symmetry in a non-generic way, okay? Which is to say we have to break it using an operator that sort of annihilates some subset of the states, okay? And many examples can be constructed using the same sort of general philosophy, okay? And I should say that this is, and I'm going to say this out loud because I think I don't know if I actually have the references written in the slides, but I should say that there are other sort of frameworks for approaching quantum scars by Mark Lin and Matrunich, and also by Mugdali et al., Bernovig's group, that have sort of a, don't work from symmetry, but have this same idea of a spectrum generating algebra, okay, an operator that kind of generates your scar states from a base state. And so I just want to be clear that, you know, the idea of this raising operator and so on was, you know, predates our work, but the kind of sort of using this observation that you can get this from symmetry to build, you know, to show that you can build many new models, such as SU3 models, Q-deform models, and so on, was our, I think, you know, major contribution to this picture. Okay, and so let me move on to the last question. So I've shown you several examples of Hamiltonians with exact quantum scars. I've told you about one way to think about their structure based on symmetry, and, you know, given you some examples that we constructed using that kind of structure. And so now let me talk a little bit about how special or unusual are quantum scars. So how fine-tuned are they? Okay, and so in order to do that, let me take a little detour, which is kind of another way of thinking about quantum scars. And so, so the general framework is, suppose that I don't want to think about symmetry. And so this, right, and so I can still start with some kind of raising operator, right, which is 0 when I take it to some power, right, so that's going to generate some polynomial in L number of states, and act on some base state, okay? And if the base state is a matrix product state, so the base state has finite entanglement, then I could say, well, here's a candidate scar tower, okay? Just generated by acting with this raising operator, whatever I choose it to be, on this matrix product state, okay? And you can actually show that, you know, as long as Q plus is one of the operators, you know, is a sum of on-site operators or certain types of kind of products of operators, you can show that these states generated in this way from matrix product states are always low entanglement states. Okay, so we have a candidate scar tower. And then you could turn this on its head and you could say, okay, so I have a set of states, I would like to make them scar states. Maybe I don't have any guiding symmetry principle. How do I find a Hamiltonian in which I can, you know, embed these as a scar tower, okay? And so now, so basically in kind of our previous picture of HC, which is the symmetric part, plus HS plus HA. So HC is now, you know, maybe we're not thinking in terms of a symmetry, so maybe it's 0, okay? HS, so I'm gonna sort of think about this operator Q plus as raising some kind of quantum number, spin quantum number, okay? And so usually an operator of this type is relatively easy to find, okay? So you can ask, how do you find HA? And there's actually a brute force method to do this. And so let me just, you know, briefly say, and let me remind you, HA is some operator which is some Hamiltonian, which basically I want it to be sufficient to ensure that the non-scar states are thermal, but it has to annihilate these scar states, okay? And so how do you find those? Well, you can actually do a kind of numerical brute force approach. So let's suppose that I want an HA, which is a sum of nearest neighbor terms. So translationally invariant and just in, you know, terms involving 2 sites, okay? So basically you can, you can write out all possible 2-site operators, right? And you can say, well, my H has to be some, you know, linear combination of these. And basically what we want to do is find all of the possible choices of these coefficients CA such that this HA is going to annihilate the scar states, okay? And there's, so actually Mark and Matrunich had an algorithm that did this. There's, we implemented a solution due to Xiaoliang Qi and Daniel Reynard, which basically says you compute a sort of covariance matrix here for every scar state psi n, okay? And you look for null eigenvectors of this matrix. And that allows you to basically brute force spit out all of the possible choices of these H's and therefore all of the possible choices of capital HA subject to the constraint that you have 2-site operators that are translation invariant. Okay. And so, you know, why am I telling you this? Simply because there are, you know, many models that do have quantum scars that don't necessarily have to be descended from symmetry. So the symmetry picture is appealing. It gives a kind of natural way in which these scars can arise. However, you know, you are free to pick, again, let me go back, and you're kind of free to pick a raising operator of your choice and a base state of your choice, you know, base matrix product state of your choice, and generate a tower of states. And you can then go and implement a numerical brute force search and write down a Hamiltonian for which these states are a scar tower, okay? So it's actually not so hard to generate models with quantum scars. And in fact, let me just sort of comment that one, you know, family of models that is most naturally thought of as being generated in this way are AKLT type scars, okay? So, and I should put the I should have put the archive numbers for these papers because there's more than one paper here by Andrei Bernovic's group. But the AKLT model is arguably the most famous Hamiltonian for which we now know that there are exact quantum scars. Okay, and they are related to a raising operator, which is minus, so a -1 to the j, and then the spin raising operator raised to the 2s power. Okay, and you can ask, and so this is a Q plus. This is a Q plus that you can think of as generating an SU2 symmetry. But these models are different from the class of models that I discussed before, because actually the base state that you use to generate your scar tower is not an eigenstate of Q squared. Okay, so this does not live in a single sort of pseudo spin representation. Okay, and okay, but okay, and so this is sort of a different class of states, and they share, a sort of different type of structure, which is which you can understand from these matrix product states, but and we constructed some general examples of these, but their relationship to symmetry is different. And so in particular, if you want to relate them to a symmetry, because this base state is not an eigenstate of Q squared, you have to actually start with a Hamiltonian that has symmetry, but also many degeneracies that are not associated with the symmetry in order for this base state to be an eigenstate. Okay. Yeah, and so I should say there's lots of interesting structure in these kind of matrix products base states as well, which is another way to sort of think about scars that I don't really have time to talk about today. So let me sort of summarize, and then I'll take questions. So the moral of this talk is that I think quantum many-body scars, first of all, are interesting. We can create Hamiltonians with exact quantum scars, where the impact of quantum scars on dynamics is observable when you start in simple states like product states. Okay, so this is not a kind of you'll never see it in the lab kind of proposition. The Hamiltonians are fine-tuned, okay, but many of them are not so unnatural in terms of models that we might write down to model realistic many-body systems. And then, okay, so those are, I think, two very important, very general messages. And then a couple of specific things is, one way to think about how this structure comes about is to think about it arising from a parent model with some kind of non-abelian symmetry. And this kind of very non-generic symmetry breaking, which sort of leaves one little multiplet alone. But there are also, that you can construct quantum scars in other ways too, starting with, as I said, a kind of matrix product state of your choice and a ladder operator, satisfying certain conditions. And many of those models are also very interesting and have a very rich structure related to the matrix product states. So let me end there and take questions.
All right. Well, thank you, Fiona. That was a great talk. And we have lots of questions actually in the chat, so we can jump to them. So I'll start with the questions that were asked kind of in the middle of the talk. So the first one is can a scar be identified using any other quantity except or other than the entanglement entropy?
So I think the most honest answer to that question is generically, I don't know. So I mean, okay, so let's, I mean, the two ways that these things definitely appear are, if you look at entanglement, or of course, if you initialize the system, in some in some state which lives, predominantly or entirely in the scar space, and then you look for these exact revivals. But I presume this question is more, directed to the idea that, well, what if I measured, for example, local observables and so on, and again, the answer is basically right. So if you look at local observables in the scar eigenstate, I just don't know. I think it's quite possible that you would see something interesting there. Of course, if you look at time evolution of local observables, not in a scar eigenstate, but in some linear combination of scar eigenstates, then you will see these revivals, and that would be a clear signature. Yeah, but in terms of other things that we usually calculate in ETH, it's a good question.
So the next question, there are basically two questions which are very similar, which is, what is the connection between these quantum many-body scars and the well-known quantum scars in periodic orbits?
Okay, good. Yeah. So there have been attempts to clarify that. Notably from Misha Lukin's group, where they were looking at these sort of quantum scars, particularly with respect to the Hamiltonians relevant to these Rydberg chains. Okay, and so they looked at things like semi-classical evolution of of states in these scar models, and argued that you see sort of periodic orbits and so on. So so you can certainly, right. So I think I think the answer is there is some connection. There's a way to try and make that concrete for specific models where you say, okay, here's my Hamiltonian, here's its evolution. I initialize the system, I look at sort of a particular kind of state, and I look at its evolution, and I look for whether I see these periodic orbits. I don't think that the connection between the two, kind of in full generality has been like fully kind of articulated and understood. But there's certainly some work on that makes clear that we do expect a connection.
Great, got it. All right. So next question is, does it make sense to use the name dark states instead of scar states, since the general definition seems to be identical to a standard definition of a dark state, which is known for a while?
Oh, okay. So I'm not familiar enough with dark states to have a good answer to that. Maybe.
Yeah. Okay. We'll see if there is a follow-up.
Maybe somebody else in the chat wants to jump in on that one.
All right.
I do think there are some similarities. So I know dark states from quantum optics, for example, where you also have many-body eigenstates that cannot absorb or emit a photon because they're also annihilated by the interaction part of your Hamiltonian. So in that sense, you also have these essentially eigenstates of symmetric models, which remain eigenstates of interacting models because they're just annihilated by the perturbation or the interaction.
Cool.
Okay. All right. So, well, in the meantime, maybe there is a follow-up to that. But in the meantime, one last question is, in these models with scars, can you always find an initial product state or an MPS with perfect revivals?
Okay. Yes. Because so the base, your base state of your scar tower is by well, okay, you could probably construct models where your base state is actually, already has logarithmic entanglement. But the models that we thought about the base state is always, either a product state or more generally a matrix product state. Okay, and so then if you act with the operator like, so you have this base state, and then the next state is like Q plus acting on that state. And so the reason that you can show that these states are all like finitely entangled is that the Q pluses you can show are, can be expressed as matrix product operators, so Q plus to the n can be expressed as a matrix product operator whose dimension like scales with n basically. Okay, so in other words, if I just take Q plus like cubed or whatever, and I act on my base state, that state is also going to be expressible as a matrix product state. And so, right, so certainly, if I know, I'm building this Hamiltonian on purpose, and I know what my base state is, and I know what my ladder operator is, then certainly you can, look at states that are just like, a superposition of two MPSs, and see these persistent oscillations.
Okay, that sounds good. I think that's the last. That was the last question. So thank you, Fiona, once again for giving the seminar and for taking all these questions that we attacked you with. And we thank, of course, the audience for participating today. Before we leave, I'll just announce next week's seminar quickly. So next week, we'll have next Thursday, which is November 19th, we'll have the seminar will be delivered by Leo Wisniewski from the University of Buenos Aires, who will be talking about signatures of quantum chaos transition in small systems and more. So with that, thank you once again, and we'll see you next week.